So, mentioned earlier that, it turned out that a long time ago, of course, people thought that everything revolved around the Earth. I mean, it makes perfect sense when you think about it. I mean, we've already seen in the planetarium and even in just our daily lives, everything seems to just rise in the east, rise overhead, and reach some highest point of above the meridian, above the southern horizon on the meridian, rather, setting in the west, and this just repeats over and over and over again. And so it's not surprising at all that ancient philosophers and astronomers like Aristotle came up with the idea of what's known as a geocentric view of the universe. They literally believed that Earth was at the center of everything of the cosmos. So here we have a statue of Aristotle. We see a drawing that was later published during the Middle Ages, so many centuries after his death, but really kind of illustrating the geocentric universe. It turns out this model of the universe, this view that we were at the center of everything, and the planets and the stars and the heavens rotated around Earth, was dominant for a very long time, a remarkably long time. So it's common to think that a lot of people thought as late as, say, the 1400s, let's say, that people thought the Earth was flat. We all heard the myth about Columbus was braving the great dangers by attempting to sail around the world when everybody thought the Earth was flat. It turns out, no, a lot of people didn't believe that the Earth was flat, and also a lot of people, or several people, didn't believe that the Earth would have to be at the center of the universe. In fact, one of the first people to propose an alternative idea by placing the sun at the center of the universe was Aristarchus of Samos. And he developed this notion that, well, maybe the sun is at the center of the universe, and maybe the planets and the Earth and the stars revolve around it. And one of the ways he was able to do this was by using solar eclipses and lunar eclipses. And you might remember this image in the lower right-hand corner. So one of the things that Aristarchus was able to do was make use of these lunar eclipses. And we looked at this image of of a lunar eclipse last week. And one of the things that Aristarchus understood was that the curve or the shape of the Earth's shadow cast upon the moon made a circular or semicircular arc. And although he didn't have the ability to take a multiple time exposure photograph like the one you see here, what he was able to do was make careful drawings and trace out over time that, oh, the Earth's shadow on the moon appears to be a circle. And there's only one object that can cast a circular shadow, and that is a sphere. So he was able to determine very early on in humankind's civilized history that the Earth must have been round. But he went several steps farther and was able to work out not only a early model that placed the sun at the center of the universe, but he was actually able to work out the relative sizes and distances of the Earth, moon, and the sun. It was a really cool feat of geometry, which is a little bit beyond the scope of what we're going to be talking about tonight. But the point I just want to illustrate here is that there were some thinkers who believed that, no, the Earth could in fact orbit the sun and could in fact be a sphere. And here are some calculations I can show you that will demonstrate the relative sizes and distances of these objects from one another. Nevertheless, Aristotle's idea still prevailed. Okay, so just to kind of look at the dates here, Aristotle, rather, I should say, was doing his thing around 360-ish BC, and Aristarchus was doing his thing around 290 to 280 BC, so a little bit later on, but nevertheless, Aristotle's ideas still prevailed, and it prevailed for a very long time. Now, one of the big problems with understanding a lot of ancient history, particularly the ancient Greeks, is that much of their information was stored in the great library of Alexandria in Egypt. And that library, you may have heard, burned down. It was attacked and burned to the ground. And so much of that information was lost. But bits and pieces of it were scattered around, and I mean literally bits and pieces of it. And there were several scholars who were able to kind of reconstruct and also just carry on the oral traditions as well as whatever they could find that was written down. And one of the people who was able to do this on behalf of Aristotle and others was a mathematician and an astronomer named Claudius Ptolemy. So he flourished sometime within around the 1st or the 2nd century of the Common Era. And he also happened to live, among other places, Alexandria in Egypt and among the Roman Empire. And so what he did is he published a great collection of works from the ancient Babylonians and the Greeks called the Almagest. And in it, he carried on Aristotle's prevailing ideas that the Earth must be at the center of the cosmos. And the idea, one of the ideas that was held very sacredly, you might say, by the ancient Greeks, was that in order for the universe to be created by the gods would have created the universe in nothing less than perfection. And so the perfect symbols, the perfect shapes would mean perfect circles for these orbits. So these orbits would be described as perfectly circular, and this idea of the planets orbiting the Earth and the sun orbiting the Earth and the stars orbiting the Earth in perfect circular arcs would dominate for about 1,500 years. So this is the geocentric universe, and this is a 16th century woodcut depicting Ptolemy's geocentric model. And Ptolemy was sort of, maybe not the grandfather of this concept, but he was certainly the curator. And his works were accepted wisdom by astronomers, by scientists, by philosophers, and even by the churches that would develop over this time, particularly, as we'll see later on, the Holy Roman Catholic Church. So in effect, everything's revolving around Earth, and you can see this woodcut. We've got the Earth at the center, and we've got the spheres, if you will, of the different planets. There's the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn. They didn't know about Uranus and Neptune, and certainly didn't know anything about Pluto. And then you had these various levels of heavens to describe the stars, and then the realm of the gods. And well, it was really interesting stuff they were able to come up with. Well, there was one problem with this view. If you take this view as you see it right here, it's still not a complete picture of all of the phenomena that were observed in the heavens at the time. One of the phenomena that was particularly confusing to people, at least at first, was this phenomena right here. What you're seeing is a sequence of images made of planet Mars in the sky. And to help, well, rather than explain what's going on, let me just show you what's going on. I'm going to switch my screen here for a moment, and I'm going to bring up this simulation right here. So by now you should be seeing, this is an image of the night sky tonight, right now, as a matter of fact. I've taken the liberty of hiding the horizon and hiding daylight so that we can keep track of things. And here, as you can see, we have Mars. Mars is right near the sun. In fact, Mars is to the west of the sun. So therefore, Mars and the sun have both set by this point, as you can tell if you look outside. So let me just show you what's going to happen. I'm going to take this date here, and rather than advance it, right now it's playing in real time. So if we sat here and waited long enough, we'd see things start to move. But we don't have all night or all day or all year. So what I'm going to do instead is just take this and advance from one day to the next, to the next, to the next, to the next. And as you can see, what I'm doing is I'm leaving behind little breadcrumbs in the sky so that we can see where Mars was. So what this means is that this is where Mars was on February 19th or 20th. Okay, and those pieces of the breadcrumbs decay over time. Okay, so I'm now going to advance it again. Let's see. And I'm going to advance by day, by day, by day, by day. As a matter of fact, you know what I'm going to do? Just to make life a little bit easier so you don't have to watch me click around all the time, I'm just going to go ahead and just play the movie by days. And I'm going to let Starry Night just do the computations for us to plot out exactly where Mars is going to appear to be in the sky. And watch what happens over these next couple of months. So we see that Mars is moving, and then it just sort of seems to stop and then go in reverse and then go forward again. That was weird. Let's just take a look at that again just to see. So I'm now going to reset the screen, or reset the scene. As a matter of fact, let me just go ahead and turn this celestial path off so you can see a little bit better. Yeah. And now I'm going to advance it by day. So each frame is going to be 1 day. And we're going to see Mars appear to go westward, eastward rather, then track back westward again, then go eastward again. You notice that Mars is changing its position among the stars, but that position changes, or the direction it changes, is not always heading eastward. Sometimes it zigzags and goes back westward. Let me run this one more time, and this time I'm going to bring it back. What I'm going to do now is I'm going to go ahead and center on Mars. And now we're just going to follow along and just watch Mars do its thing. And now I'm going to turn those breadcrumbs back on so we can see this a little bit better. And now we're just going to watch our show. So Mars is now zigzagging, heading back westward again, and then it'll appear to track eastward once more. And you can watch the dates here. So that was this year, and then November, December, now we're into January of next year. Here's the sun. Mars is getting closer to the sun. Pick up a little lens flare. Okay, fine. Nice of starting it to do that for us. And now we're going to be making our way around the sky once again. And now we're into 2018. And we're going to see Mars execute another back and forth motion. How about that? So ancient Babylonians were keeping track of these. Types of observations. They were watching Mars do this. They were carefully recording in the sky what was happening. And so this sort of motion has a special name, and it's called retrograde motion. Okay, so if you have all of the planets revolving around Earth, with Earth fixed at the center, there's no way you could ever have this kind of motion. So something was needed to explain retrograde motion. And the interesting thing about this is that Ptolemy was pretty clever, and he was able to work out some stuff. And what he did is he introduced this concept. It's a concept known as epicycles. And so what he does, he says, okay, rather than have the planets directly orbiting the Earth, what they're going to do instead is they're going to rotate around on something called an epicycle. And the epicycle, in turn, follows a path around the Earth called a deferent. And what Ptolemy was able to do was, by comparing these observations to his model, he was able to kind of fine-tune his model to make the retrograde cycles of Mars occur at the same time and for the same duration as when these retrogrades of Mars were observed. It wasn't as simple, though, as just directly having the epicycle and deference centered on the Earth. No, what he had to do is he had to then take the Earth and separate it from the very dead center of the universe, and he had to have the epicycle and deferent revolving around another point offset by the same amount on the other side of the center, called an equant. Knowing this stuff to this level of detail is not necessary. What's important to understand is this is just an example of the kind of geometric hoops and tricks that Ptolemy had to resort to. As a matter of fact, let me just show you this animation right here. This is here we have an equant with the Earth offset on the opposite side of the center. We have a deferent, and on that we have the epicycle of Mars. And what Ptolemy found was that if he could just set these values, set the diameter, set the size of the epicycle and the distance to the equant and the size of the deferent just right, he could make Mars execute what would appear to look like from Earth one retrograde cycle at the same time and at the same duration as observed. All of this was well and good, and to be honest, it was actually a really cool tour de force of Ptolemy's geometric chops, right? His ability to use some mathematics and some geometry to come up with a working model that could not only explain the previously seen retrogrades of the planets, but he could also use that to predict, to a reasonable degree of accuracy, future retrogrades of the planets. So, you know, good on Ptolemy, right? It wasn't all that bad. But there were, however, some problems with the idea of epicycles. I mean, over time, if you didn't adjust your epicycles or maybe tweak the size of your deferent circle or your the spacing of your equant or these other things, over time these retrogrades would not quite arrive at the same time as predicted by the model. Another problem was the sheer complexity of all of this. I mean, you had to have all kinds of epicycles, each with their own unique combination of settings, each finely tuned to describe the motions of the planets. It wasn't very elegant. It was rather complex. And people had begun to start to rethink about this earlier idea from Aristarchus and others. What would happen if we just placed the sun at the center? Could we explain this sort of phenomena? And a lot of people began to think about it, but the first person to ever come up with a really truly mathematical approach to this idea was a mathematician and astronomer named Nicolaus Copernicus. So now we're somewhere into the 15th or 16th century Poland, and he was the one who actually did the math for the first time. And as we're going to learn later on throughout this course, you know, mathematics really does appear to be the language of the universe, does appear to be the language of the cosmos. So if we can understand the math well, we can understand the universe very well. Now, I'm not going to go into all the mathematics here. That's a little bit beyond the scope of tonight's discussion, but we'll delve into some of it later on, so don't worry. But let's take a look at Nicolaus Copernicus's early model. Well, he published it in a book which is translated into On the Revolutions of the Heavenly Spheres in the 1500s. And he places the sun directly at the center, followed by Mercury, then Venus, then Earth and the Moon, Mars, Jupiter, Saturn, and then the stars. Again, no one had discovered Uranus or Neptune yet, so these were all of the known planets at that time. So let's see now if we can use Copernicus's model, and let's apply that to this strange phenomena of retrograde motion. So we're going to begin, and we're just going to use Earth and Mars as a comparison, but you can do this for any planet. But we have here Earth and Mars. You'll see Earth, of course, is orbiting inside of Mars's orbit. Another way to think of this is that Mars and Jupiter and Saturn are considered superior planets. In other words, they orbit the sun at a distance greater than Earth orbits the sun. Venus and Mercury, on the other hand, are considered inferior planets. They orbit the sun at a distance closer to the sun than we do. Okay, so here we have a superior planet, Mars. And if you're on Earth and you look up and you see Mars and you're in this kind of arrangement, well, remember, we're looking at this from above the solar system. From Earth, what we do is we can now project that point of view of Mars, and we see that it arrives at the indicated position amid the fixed stars. These are the stars of the celestial sphere that we learned about. Now, later on, if we allow a certain amount of time to pass, Mars is going to move along in its orbit by a certain amount, but because Earth is on the inside track, it covers a greater distance in its orbit in the same amount of time. So let's say, just for the sake of argument, that this was 1 month of travel of Earth and Mars around the sun. We find that Earth is gotten a little bit farther along in its orbit than Mars has gotten along in its orbit. And now, when we look up at Mars, we see that Mars has apparently shifted, in this case, further toward the bottom of your screen, or if you think about it as looking at it from Earth, further toward the eastern direction in the sky. Then, however, when Earth begins to catch up with Mars, or catches up with Mars, Mars now appears to have shifted backward or westward in the sky. So Mars is now in retrograde motion. As a matter of fact, we let this thing continue for another couple of weeks. Earth now begins to overtake Mars, and in so doing, from our perspective on Earth, Mars appears to have shifted farthest west, full retrograde, but then as Earth continues to move along, so does Mars, and Mars has come out of retrograde. It is now moving eastward again. So now we have retrograde explained completely differently. Rather than complex epicycles and equants and deference and all these things you have to finely tune, retrograde is instead an apparent motion. It's not that Mars is physically changing its direction. It's just, it seems like it's changing its direction by virtue of the fact that we are simply on an inside track around the sun. So when Earth overtakes a superior or outer planet, you get retrograde motion. Likewise, if an inferior or an inside planet closer to the sun, Venus or Mercury, overtakes the Earth, they appear to execute a retrograde motion. And that's all it is. So this was a pretty controversial idea. This was pretty radical and pretty crazy. And a lot of people, well, they didn't really know if this was really true or not. You know, after all, everything rises in the east and sets in the west. Can't we just explain it that way? Why do we need to have the sun at the center? It doesn't seem the way, well, like in the old days, it was the gods, and by this point, it was probably just the one god that a lot of people believed in. It doesn't seem like God would do that. So there was a man who really had a really sophisticated observatory for his day, and he did something really interesting. Rather than debate the question back and forth or try to use logical reasoning, what he decided to do instead was test the idea, see if he could actually make some observations which would help prove or lend more credence to one point of view or the other. And that man's name was Tycho Brahe. He lived in Denmark. He was an extremely wealthy person. Now, as an astronomer, it's important to remember that at this time in history, no one had yet used a telescope on the heavens. So his instrument, his prime observing instrument, was his eyes. That was it. But to help him understand exactly where he was looking in the sky, he commissioned these very elaborate murals. As you can see here, we have a nice mural that, by the way, featured him discovering the universe. I guess Tycho was pretty impressed with himself. But on the mural, he also had the degrees of a circle. And we learned about a circle of 360 degrees being further divided into, each degree is further divided into 60 minutes of arc. And each minute of arc is further divided into seconds of arc, 60 seconds of arc. Well, you and I cannot really observe the heavens at the arc second level. It's very difficult to detect those changes, but we can certainly get to it then a few arc minutes. Point being is that this was the state of the art back in the day. Okay. And he did something that no one else had been able to accomplish, and that is he took data, lots and lots of carefully, meticulously measured data. And this was a revolution in science. This was the first time anybody had really ever taken a measured approach, literally trying to measure things and record what they were measuring in a numerical manner. There's just one problem, though, and that was, for all of his wealth and for all of his observing acumen, Tycho really lacked the mathematical skills to be able to properly analyze this data and test these two competing ideas. So he needed help. He had to hire a mathematician to assist him. And he found somebody, and his name was Johannes Kepler. Johann Kepler was living in the Holy Roman Empire of Australia. He thought the heliocentric model was probably the one that was correct, but he also firmly believed that these orbits of the planets must be in perfect circles surrounding the sun. Again, because this is the way God would create the heavens. Didn't make sense to have him create it in any other way. Moreover, he also had this idea, being that he was a mathematician, that if you could take the so-called platonic solids, these are the solids where each side can be exactly equal to another. So for example, a cube is composed of 6 equally sized squares. You know, a dodecahedron is composed of 12 equally sized hexagon. So you get the idea, right? And what he worked out was that if he could nest these geometric solids inside of each other in a very specific pattern, then draw a circle or through each of the corners of each of these geometric solids, that the planets would orbit in circles at exactly these relative locations around the sun as dictated by these Platonic solids. Again, he believed that math was the language of the universe and therefore the language of God. So if he could understand this, he could understand the mind of God. So Tycho Brahe learned of this young mathematician and asked him, please come work for me. I need your help. So he did. He moved his family up to Denmark. He worked with Tycho Brahe. Now, Tycho Brahe was a very intelligent guy. He was a very wealthy guy. He was also a pretty proud guy, too. He actually wore a bronze nose because he had his original nose shot off in a duel because I think they were arguing over whether the planets orbited the Earth or if the planets orbited the sun. So the good news is that today we don't settle scientific questions by duels, but that's how they settled it back in those days. And so Tycho Brahe was pretty hardcore. He was also pretty proud. He was so proud, in fact, that he didn't want to give this young mathematician all of his data. He was afraid that this Kepler fellow would learn something important about the universe and would publish it, and he wouldn't get credit, and Tycho wouldn't get credit for it. So he kind of gave Kepler just enough data to do his work, but not quite all of it, Well, then one day, Johann Kepler caught a huge break because Tycho died. And when Tycho died, Kepler went to Tycho's widow and said, may I please have the rest of the data? And she said, sure. And he said, I'm now going to prove, I'm going to see if my idea is correct. I'm going to see if the universe is arranged in this manner according to the relative outlines of these geometric solids, and that the universe behaves exactly as I had hoped. And what he discovered was that it did not behave as he expected, that the planets did not orbit the sun at perfect circles at these exact locations. And he wanted to believe this idea very, very deeply that they did. I mean, this was quite literally a deeply held religious belief of his. Well, just as Tycho Brahe was really important in history for testing ideas through observation, Kepler is also one of the first true scientists to do what is very, very difficult for human beings to do. And that is, he abandoned his deeply cherished belief in how the universe must be ordered, and instead looked to see what the data and his calculations were telling him. And what they told him, he published these ideas as 3 empirical laws of planetary motion. Now, what do we mean when we say an empirical law? Well, an empirical law explains what's been observed. It doesn't purport to explain how it works, or even a quote, why it works. He's just basically saying, hey, I have crunched my numbers very, very hard. I really worked hard on this, and these appear to be the laws of planetary motion. I don't know why they work this way, but they do. And here are the laws. The first law has to do with the idea that planets follow the path around the sun, not in a circle, but in another kind of a shape called an ellipse. So let's talk about the differences between ellipses and circles. If we want to draw a circle, okay, all you have to do, as you see here in the illustration, is you hammer a nail or a tack or something like that into a piece of paper. You tie a string around it, around the nail, and you tie the string around a pencil or a pen. You hold the pencil out and then just do what comes naturally, right? You create a perfect circle. So we know that the blue line describes the circle's diameter, and 1/2 of that line, in other words, the distance from the very center of the circle to the very edge, we give that a special name. We call that the radius. What if instead of one nail, you hammered two nails into the wall? And you tie a piece of string around that and the pencil, and then you pull the pencil and the string taut, and then do what comes naturally. Well, now you have an ellipse. So the positions of the nails create something not called the center, but instead create a position each called the focus, or plural foci. So we have an ellipse is a shape with not one center, but two foci. There's also a couple of lines here that are worth pointing out. The first, of course, is the red dotted line. That has the name known as the major axis. The blue dotted line has another name called the minor axis. Now, whereas we look to the radius as being 1/2 of the diameter, or rather the distance from the center of the circle out to the circle's very edge, in the case of an ellipse, the distance from the center of the ellipse to the outer edge of the major axis is called the semi-major axis, or semi-major axis. Okay, so those are the three components of an ellipse: the two foci, the minor axis, semi-major axis, four components, and the semi-major axis. It's the semi-major axis that we're going to come back to in a little bit in Kepler's third law. But right now we're talking about Kepler's first law, and that is all planets orbit the sun in a path that is an ellipse. But before we get into that first law, let me also just make one more point about ellipses. If we take the two nails and we bring them closer together, the ellipse is going to get a lot more circle shaped. It's going to start to resemble more and more of a circle. In fact, if you put two nails on top of one another, well, that's the same thing as just having one nail, and you get a perfect circle. Likewise, if you take those two nails and you separate them farther and farther and then draw another ellipse with the pencil, the ellipse is going to get skinnier and skinnier, or more elongated. Well, we measure how elongated an ellipse is by using a term called eccentricity, and we abbreviate that with the lowercase e. So eccentricity it's just a number. It's not measured in meters or distance or time or weight or anything like that. It's just a number. And it's a value, in the case of an ellipse, between 0 and 1. So if you have an eccentricity of 0, you have a perfect circle. Maybe a moderately eccentric ellipse is 0.2, and then there's another example at 0.4. What are some real-world examples? Well, let's compare the Earth to Pluto. I chose these two planets because they have two very different eccentricities. The Earth, as you can see, is very, very, very close to a circle. It's not exactly a circle, but it's awfully close. Just a low eccentricity of just about 0.017. Pluto, on the other hand, as planets go, it's considerably more eccentric. In fact, the most eccentric of all the planets at 0.3. So now you have a different definition of the word eccentric than you're probably used to, but this is the mathematical definition of eccentricity. So what Kepler says is, he says in his first law that a planet orbits the sun in an ellipse, and the sun occupies one of the two foci. So planets orbit the sun in an ellipse with the sun at one focus and nothing at the other focus. There's no anti-sun, there's no black hole, there's no... The second focus of a planet's orbital path is just a point in space. There's nothing there, nothing physical there, and so it doesn't even get a special name. So if we take a look at our planet, you see it orbiting the sun in the ellipse, that means at one point in the ellipse, it's going to reach its closest distance to the sun. And that distance, that point of closest approach to the sun, has a special name. It's called perihelion. Meanwhile, if we let the planet continue to orbit until it finally reaches, on the far right-hand side of your diagram, its farthest distance from the sun, that position is called aphelion. So that was Kepler's first law. Now let's take a look at Kepler's second law. What he discovered was that a planet moves around in its orbit, but as it does so, it sweeps out an equal area in an equal amount of time. Let's break that one down a little bit. So we have the planet beginning at the top of the diagram. You see on the far left, on the left there, you see it having a starting point at position A. That would be at the top of the diagram. And then if we allow a given interval of time, let's just say it's exactly 30 days. I'm making up a number here, okay? 30 days later, the planet has swung around to the bottom position that you see. And if you were to actually connect the dots and shade that area in orange, and then calculate the area, you'd have that number, and that area is called area A. Likewise, if you allow the planet to continue to move in the orbit, and let's go to just the right-hand side of the diagram, starting at the bottom in the green section on the right-hand side at position C, let's let 30 days go by. It's not going to move as far along in its orbit, but if you connect the dots with the final position 30 days later, and you shade in the area, and you measure that area, you find that it's exactly equal to the area A. As a matter of fact, if you took any 30-day interval of time and you worked out the area that the planet sweeps out, you'd find that that area is always equal. Now, to help you visualize this a little bit better, let me switch from the presentation to a simulation. Okay, so let's see what we have here. So we're going to take a look at Kepler's first and second law. Okay, so I have a planet. As a matter of fact, it's the planet Mercury, and we have its orbit drawn out. Let's see. Well, actually, this isn't exactly the orbit of planet Mercury because here we are. This is the orbit of planet Mercury. Okay, so we have a semi-major axis of 0.4 astronomical units. Remember, the Earth and the Sun are separated by 1 astronomical unit. So Mercury is 0.4 astronomical units. It has an eccentricity of about 0.2, fairly eccentric, okay? And you'll see that the Sun is not dead at the center, but it is in fact slightly offset. Let me go ahead and point out the center of the ellipse. And if you're curious, that is the position of the empty focus. Again, there's nothing there. It's just there for our illustration, but there is no object there. Okay, so we can now draw in the let me just draw the semi-major axis. To tell you the truth, I'm showing you the semi-minor axis. In astronomy, we really don't care about the semi-minor axis. It turns out that the semi-major axis is good enough. It also, another little pro tip, the semi-major axis is sufficient to consider the average distance of a planet from the Sun throughout its orbital period. So we're going to be using semi-major axis quite a bit. Okay, so let's go ahead and just start the animation. Okay, let's just watch our planet do its thing. All right, now what I'm going to do is I'm going to slow it down a little bit here so we can get a better view of it. And if you're watching Mercury orbit the Sun, you're going to you may notice that it speeds up slightly as it gets to its closest point to the Sun. That's called perihelion. You'll recall it's perihelion. And it seems to be moving slowest when it's at aphelion. So let's watch Mercury perihelion, and it's moving a little bit quicker. And then as it swings out, it seems to be maybe just ever so slightly slowing down. Now, we can demonstrate this instead of just letting you watch this. We can now switch over to Kepler's second law. Okay, and what I'm going to do is we're going to sweep in consistent intervals, okay? So every 16th of an orbit, we're going to make a mark, and at the next 16th of the orbit, we're going to set another mark and shade that in. So let me just go ahead and sweep at some random spots. There's one, and let's do another one. There's another. Okay, so we have 2 sweeps that I've more or less arranged to get us somewhere around perihelion and aphelion. And if you were to measure the amount of time it takes to go from here to here, you'll see that it exactly equals the amount of time it takes to go from here to here. Okay? Let's see. If I sweep this continuously, let me erase the sweeps. Let's go ahead and see what happens. Now we're just going to let it draw out. And if you were to measure the areas of each of these triangles, they will all equal one another. So not only does A equal B equals C, but A equals B equals C equals D equals E. In other words, you can, no matter how small you make these sweeps, let me do this again. And let's erase the sweeps again. Now I'm going to adjust the size to be even tinier. And if we start sweeping, if you took these triangles and you were to measure their areas or calculate their areas, you'd find they all equal one another as well. So it doesn't matter how fine you slice the pie, every pie shape gives you the same area. And why is that? Well, that's because the planet is moving quicker as it approaches perihelion and moving slowest when it reaches aphelion. Let me give you one more example. Might be a little bit easier to depict. We'll go to Mars. Actually, we'll do Pluto since it's got a nice, yeah, okay. So Pluto has the highest eccentricity, and I'm going to really have to increase the animation rate because we're talking about Pluto here. Boy, it's slow. Yeah. Actually, I'll tell you what I'll do. We'll go, let's use Earth. We'll do this. And now what I'm going to do, oh boy, look at that, right? So I better slow this down. Slow it down a little bit here. Here we go. So Earth is very, very close, has a very low eccentricity, you know, almost 0.02. Okay, it's very low. It's almost a circle. And as you can see, the areas appear to be similar size, but they're in fact all the same size. It's just that, I'm sorry, the areas look completely even, and they are the same value. But some of these are slightly skinnier than others. And to help you visualize that better, I'm going to go ahead now and just take Earth's eccentricity and really, really crank it up. Okay, I'm going to really exaggerate it here just for the purpose of illustration. Let's erase the sweeps. Let's increase our animation rate. There we go. And now you can really see it pick up speed as it approaches the sun at perihelion. And it really seems to slow down as it reaches aphelion. So again, we start sweeping. Kind of psychedelic, isn't it? Anyway, that is Kepler's second law in action. So you notice that Kepler's second law is true every area swept out by the planet over a given time interval, as long as the time interval is the same. So in other words, if this is 2 weeks and this is 2 weeks, and all of these are 2-week intervals, as long as that time interval is the same, the planet is going to sweep out an area that is exactly equal to every other area in its orbit swept out over the same time interval. Okay, equal areas in equal times. And that's Kepler's second law. So now, Kepler's third law is what I want to talk about next. And what he did is, we saw in that second law that there appears to be well, actually, you may have noticed during the demonstration. Let me actually switch back to the. Let me switch back to this really quick. I want you to consider something here. I'm going to show you Earth, okay? And we have Earth, and as you know, it will take 1 full year, what we call a year, for Earth to make 1 complete orbit around the sun. However, we find that for Mercury, the orbital period is about 88 days. And for Pluto, the orbital period is about 240 years. So there seems to be a relationship between the orbital period of a planet, how long it takes to revolve around the sun, and its distance from the sun as measured by its semi-major axis. Kepler was aware of this relationship, and he was able to discover a mathematical law that describes this relationship perfectly. And here it is. What he found was that if you take the value of the orbital period and you square that number, okay, measuring it in years, okay, it turns out that's exactly equal to the cube of the planet's semi-major axis when measured in astronomical units. So here we have a planet around the sun. It has some period in years, and we have it's at some semi-major axis measured in astronomical units, and we can express this mathematically by saying p squared is equal to a cubed. This is a very important law. We're going to be working with this law quite a bit throughout. But what this is saying is that if you have an outer planet, let's say, okay, it's going to take longer to orbit the sun, regardless of the fact that it's not just because it has a longer path, it is literally moving slower. So when this planet, this outer planet, reaches perihelion, it's not going to be moving around the sun as rapidly as the inner planet when it reaches perihelion. Okay. Similarly, when the inner planet reaches aphelion, yeah, it's going to be moving at its slowest speed of its orbit, but that is still going to be much quicker than the aphelion of the outer planet. So the farther away you are from the sun, the slower your average orbital speed. In other words, the period value squared goes as the planet's semi-major axis cubed. As a matter of fact, though, if you take the ratio of these two values, they equal 1. I mean, after all, if you take p squared and divided it by a cubed, well, since those two numbers should equal one another, a number divided by itself is exactly equal to 1, right? So it turns out that you can plot this, and you can plot out, we have the Earth, the orbital period that's measured in Earth years. Okay, so we have 10 to the minus second. You remember we briefly talked about scientific notation earlier, so this is the same thing as saying 0.002, 10 to the 0 is 1, 10 to the second is 100, 1,000, I'm sorry, 10,000, and then finally 100,000. I'm sorry, 1 million, excuse me. And then you have the same value in astronomical units. The point is that you get a perfectly linear plot, okay? The two numbers exactly equal one another. This idea that the two values equal one another, you know, was used to describe something called the music of the spheres. In other words, there was a harmonic law that could be implied here. Simply that the ratio of these two values always comes out to equaling 1. So we'll be using Kepler's harmonic law a little bit later on. So that concludes the discussion on the early history of astronomy, you might say, and also understanding the motions of the planets, at least up to the time of Johannes Kepler. Are there any questions at this point? Okay, so what I'm going to do is I'm going to pause the recording. Why don't we take a few minutes, and then we'll come back. I'm going to go get a little something to drink. Feel free to knock yourself out for about 5 minutes or so, and then we'll pick it up after this. I'll just leave the Zoom running, and I'll just end the recording now.